going to be talking about large-scale confidence intervals for the proportion. The scenario of the proportion is that we have categorical data, or more specifically binary data, that is true or false. And here, in this situation, the number of successes in a sample, that follows a binomial distribution, and for large samples in a fixed number of trials, the sampling proportion or distribution can be approximated by this normal distribution. Now, there are a couple of caveats to ensure that this approximation is a good one, and that means that we have to have the number of observed data times the probability of success is at least 5, and that n times 1 minus p is greater than 5 as well. Okay. So if these methods aren't met, you need to use the binomial distribution to try and make conclusions about your data. Okay. So why can we use the central limit theorem for the sampling proportion? So here the sampling proportion is the total number of successes out of n trials, and so we have n Bernoulli observations, so 0, 1 outcomes are true or false, success or failure. And you can think a Bernoulli is a binomial distribution with n equal to 1, repeated n times. And recall that the mean of the Bernoulli distribution then is p, and the standard deviation is p times q, or p times 1 minus p. If you invoke the central limit theorem and you have a large enough sample size, then the sample average, which is just the total number of successes, the sum of all the outcomes, which is just 0 or 1s, where you can think the total number of successes in this instance, divided by the total number of outcomes n, t over n, in other words, is equal to what we call p hat, the sample proportion. The sample proportion then has mean p according to the central limit theorem, and the standard deviation is that you take the old standard deviation and you divide it by the square root of n, which gives us this formula. Hence, this quantity has a standard normal 0, 1 distribution by the central limit theorem. Okay, so if we're interested in deriving a confidence interval, say a 95% confidence interval, in this case alpha is equal to 5, then just like we did with the normal distribution in previous instances, that means that 95% of our data lies between z sub alpha over 2, negative, and positive z sub alpha over 2, and this probability is 95%. So in other words, the sampling distribution minus the true mean divided by the standard deviation has 95% probability to lie between these two values. Now, if we solve for the population mean, which in this case is p, the sampling distribution p hat can be observed. That's p hat over n. The sampling distribution is t over n, the total number of successes, and we estimate the standard deviation with p hat times 1 minus p hat over n. Then we can arrive at a confidence interval for the population proportion of successes, and it's given by this interval. Okay? So, in what happens next, we define a function to calculate this confidence interval, okay? And I'm not expecting us to completely understand this code because this isn't a coding class, but what this returns is it returns the sampling proportion p hat. It returns the lower estimate, that's this quantity, that calculation, the upper bound, that's this part of the confidence interval, and it also returns the margin of error. The margin of error is just this quantity right here. Okay. Okay. So suppose we have 100 automobile engines with crankshaft bearings, and x equals 10 has a surface finish that is rougher than the specification. We can compute a 95% two-sided confidence interval for the population proportion. Okay. Okay. So if we calculate this, we plug in x is 10, n is equal to 100 samples, and we want a 95% confidence interval. So out of 10, we observe 10 that were successes out of the 100. Okay, and so we can calculate the confidence interval here is going to be this 0.041 as the lower estimate for the proportion of defectives, up to this higher estimate of 0.159. Okay, and how we got this is just by using this confidence interval formula. We didn't have to use Python. We could have just used the normal calculator, plugging in these values, and that would give us this. Okay, arriving at the same confidence interval. Now, the sample size can be useful for determining the error in the estimate. Okay, so suppose we want a maximum an interval that is small. So, for example, the width of the interval. So this, has this margin of error. Suppose we wanted to decrease this margin of error. We can better estimate the proportion if the sample here is larger. If n is large, that makes this plus or minus quantity a lot smaller. So how small do we need to be it? Well, we can calculate it with this equation. And if we don't have an estimate for what p is, we can obtain an upper bound with this formula. Okay, so the formula here tells us that we can control the width of our interval by collecting a sufficient number of samples. Okay, so this is the function that tells us how many we need to calculate. And in this example, suppose we have n is 100, x is 10, and p hat is 10. We want to know how large of a sample is required. If we want a 95% confidence interval, we have to be told the level of confidence so that the margin of error for p hat is less than 0.05 or 5%. So we're going to use this estimate of 10% for p in this first instance. In the second instance, we're going to not use an estimate of p. Okay, so we're going to pretend we don't have one. Okay, so if we want our error to be 5% or 0.05, we have 95% confidence interval. Okay, we're going to estimate p as 10%. Then we can calculate n using this equation. And we see that we need 139 samples in this instance with p equals to 10. If we don't have an estimate for the proportion, okay, we can use that second formula here, and that essentially is setting p equal to 0.5. Okay, so then the number of samples we need is 385. That's a lot more than 139, but that's because we don't know what the proportion value is. Okay. Okay, so in this second example, the weights of 200 rats are measured under experimental controls, and that there are 10 underweight rats. We want to create a 90% two-sided confidence interval on the true proportion of rats that would show experience the category of being underweight from this experiment. Okay, so our sample size is 200. That's the number of rats. The proportion that was observed, the number that was observed to be underweight is 10. We want a 90% confidence interval. Okay. So our point estimate for the number of rats is 0.05. That's 10 divided by 200. And the confidence interval for P is 2.5% all the way up to 7.5%. Okay. Now suppose we want to find the confidence interval for voter proportions. Okay, so this is a different example. Suppose we have 250 randomly selected voters, and we have 125 voters that are in favor of a school bond measure. The first question we're going to ask is, what is the sample proportion? What's the observed number in favor of the bond measure? Well, that's just 125 divided by 250, and that gives us 50%. Okay, what's the error in this estimate? So if we want to use a 95% confidence interval, our margin of error is about 6.2% in this poll. Okay, because of the confidence interval. Okay, so this is the exact formula being worked out here, and our confidence interval for the sample proportion would be anywhere from 43.8% to 56.2% using this data. Okay, thank you very much.